Hey everyone, welcome back. So we're talking about turbulence, right? So we left off last time and we decided that we wanted to still be able to model turbulent flow using differential equations that we kind of originally started with for boundary layers. But when we're in a turbulent type flow, we have these additional things happening. It's not just well-behaved laminar flow. There's other things happening. There's movement. Normal to the surface, right, in the y direction. And so we need to come up with additional terms to deal with that. All right, so this is a quick recap of, we kind of got into this averaging thing to start, but basically we said, okay, let's pick a location here in our boundary layer. And at that particular point, let's plot out the velocity. And if you plot the velocity, there's kind of two components to the velocity. There's an average component, which doesn't change over that time interval. And then there's the variability around that average component. So if we break up our velocity profile into those two things and then treat them separately, maybe we can come up with some additional terms in our governing differential equations that help us actually characterize kind of the average turbulent condition. All right, so this is, just to refresh ourselves on what we were doing. We broke up into these terms. I kind of have crossed out what I was doing, but so we have our U, our V velocities, and we say those velocities are the average, which is just a function of position, right? The average is not changing with time, plus the variability, which we designated U prime or V prime. And so the variability, right? That's the little deviation around the average that's happening. So if you look at that deviation or that variability, that's going to be centered symmetrically around zero. So that if you integrate from whatever the time equals zero up to your time window for averaging due to integration, that integral of U prime should be zero. The average above the line, or the amount of area above the line, should equal the amount of area below the line for U prime. And that's true for U prime, for V prime, and for temperature. And I guess I wrote this out before I came in, but basically the same thing for temperature, which is the average just as a function of position, plus the variability component, which is T prime. Okay, and we just define the averages this way, where we say it's the time integral from 0 to T int. And again, T int is going to be something that we have to decide, right? We have to basically choose that to be longer than the time scale of the turbulence fluctuations, but shorter than, let's say, if this problem is changing with time, let's say there's a non-steady state condition or something like that. If it is changing with time, we have to make sure that our averaging is over a short enough window where we're not capturing those longer term effects. Okay. So it's just the time average, and then you divide by the time interval T int to get back the average value over that interval. Okay, so this is kind of as far as we got, I think. So what we're going to do is we're going to take these definitions. We have now U, V, and T in terms of X, Y, and T. And we're going to now substitute these into our differential equations and go through the process of trying to simplify out, get rid of things we don't need, and see what's left over at the end of this process that we're going to need to include in our Reynolds or in our differential equations. Okay. So as we usually do, let's start with the continuity equation. Again, we're going to take this equation, we're going to substitute our new definitions of U and V in here and go through the process of simplifying out and see what we're kind of left with. Okay, so to start here, let's, for continuity, let's say we know that U, X, Y, T, that's the real velocity as a function of space and time. That's going to be approximated for us as U bar, which is just a function of space, plus the variability U prime, which is a function of X, Y, and time. Okay, so we're going to take that definition and this whole thing here, we're going to substitute this in for U. Okay, we're going to do the same thing for V, where we'll say V bar XY plus V prime XYT. That whole thing gets substituted in here for V. And then we can go through and kind of see how it plays out. So we'll drop the XYT thing from our subsequent versions of this, but let's write out what we have. So we end up with the partial, so U becomes U bar plus u prime with respect to x plus the partial of, oops, not y, the partial of v bar plus v prime with respect to y, that equals 0. Okay, so then what we want to do is we want to get rid of this v prime or u prime and v prime. We want to get rid of the variability that we're seeing in this equation. And how do we do that? Well, we integrate over time. So we're going to take this equation here and we're going to integrate this whole thing from 0 to t int, right, with respect to time. So we're integrating that whole equation with respect to time. And then to get the time average, we have to divide by 1 over t int. There. Okay, so we can actually now take this, we can break this up into 4 integrals, right? We have du bar dx, du prime dx, dv bar dy, dv prime dy. Each of those 4 things is a linear problem, so we can separate them out and do those integrals separately. So let's just write it out that way. So we have now 1 over t int times the 4 integrals. So that's going to be 0 to t int of du bar dx dt plus 0 to t int of du prime dx with respect to, or times d time, plus the 3rd integral is going to be, let's see, 0 to t int of dv bar dx d time, plus the last one is 0 to t int of dv prime dx with respect to time. Okay, hopefully got all that. Dx. Let's see. That should be dy, right? This here. dv bar dy and dv prime dy. Right, because we're just splitting up that integral. Okay. So then why do we do that? Well, we can go through and now let's look at each of these things and try to think through what is actually happening in each of these terms as we take the integral, right? Let's look at, let's look at this term here first. So if we do this integral, this is going to be 1 over t int of the integral from 0 to t int du bar dx dt, that's equal to, let's see, so du bar, right? U bar is something that's not changing with respect to time, right? So in fact, du bar dx is something that's not changing with respect to time. So that can come out of that time integral, right? So if we do that, that ends up being just, let's see, 1 over t int times du bar dx times the integral from 0 to t int of what's left, just dt. Okay, so if you do that integral, the definite integral here, this is just going to be equal to t int. All right, and so then we're just left with what? We're just left with du bar dx. All right, that term just becomes du bar dx. Hopefully that makes sense. Okay, let's see. Let's do a different term here. I'm kind of running out of room, but let's do this one here. I'll draw it with red. So let's do the second term here, du prime dx. And let's think about what's happening there. All right, again, so you almost can by inspection see what's going to happen here, right? We know that u prime is variability around, in this case, 0. If we take the integral of that variability, by our definition of what we're doing here, we should have that be 0, right? That term should be 0 because we're just taking the integral of u prime with respect to that derivative with respect to time. So that should be 0. So in fact, we'll just write it out that way. So this becomes 0. So we could do the same thing for v. I don't think we need to do that, but you end up with v bar being just going to the average value, and then v prime goes away as well. So if we rewrite our continuity equation, having made this substitution, we end up with du bar dx plus dv bar dy is equal to 0. All right. So some, kind of steps for that, and we end up with kind of like it's kind of anticlimactic, right? Like we've just basically said that we've basically restated our original continuity equation just in terms of the average value. But it's actually telling us kind of something important here, which is that the variability component in the turbulent flow doesn't affect the overall governing equation, right? We only are concerning ourselves with the average condition. And we can write the continuity equation that way and not have to worry about anything else in terms of variability for continuity. Now you're going to see that's not the case for some of the other equations that we're going to use, okay?